Hi, I'm Miss Barber. The title of this lesson is Sequences and Summation Notation. The learning objectives for this lesson are 1. Be able to define and recognize sequences. 2. Be able to evaluate recursively defined sequences. 3. Be able to compute partial sums of a sequence. And 4. Be able to use the sigma notation. Roman numeral 1. Sequences. A sequence is a function f whose domain is the set of natural numbers. The terms of the sequence are the function values f of 1, f of 2, f of 3, f of n, . We usually write a subscript n instead of the function notation f of n, so the terms of the sequence are written a sub 1, a sub 2, a sub 3, a sub n, comma, . The number a sub 1 is called the first term, a sub 2 is called the second term, and in general a sub n is called the nth term. To specify a procedure for finding all the terms of a sequence, we can give a formula for the nth term of the sequence. The presence of -1 to the n in the sequence has the effect of making successive terms alternately negative and positive. Find the first 4 terms in the 100th term of the sequence defined by a sub n equals 3n plus 1. So let's find them. A sub 1, that's the first term. We're going to put in 1 for the n, plus 1. And 3 plus 1 is 4. A sub 2, B3, and we put in 2 for the n. 3 times 2 is 6. 6 plus 1 is 7. A sub 3 is 3 times, we put in 3 for the n, plus 1. 3 times 3 is 9. 9 plus 1 is 10. And a subscript 4, that's the 4th term. 3 times 4 plus 1. 3 times 4 is 12, and 12 plus 1 is 13. And now we want the 100th term, which would be 3 times 100 plus 1. And 3 times 100 is 300, and add 1, so it'll be 301. Let's go to part B. C sub n equals n squared plus 1. The first term, C sub 1, is 1 squared plus 1. 1 squared is 1. 1 plus 1 is 2. C sub 2 would be 2 squared plus 1. 2 squared is 4. 4 plus 1 is 5. C subscript 3, that's the third term of the sequence, C. So we would have 3 squared plus 1. 3 squared is 9, and 9 plus 1 is 10. C sub 4 would be 4 squared plus 1. 4 squared is 16. 16 plus 1 is 7. Ooh. And C sub 100 is 100 squared plus 1. 100 squared is 10,000. Add 1 to 10,000 and you get 10,001. Continuing. B sub n is defined as the quantity n minus 1 divided by n. Let's find the first term. B sub 1, so we'll have 1 minus 1 over 1. 1 minus 1 is 0 over 1, which is just 0. B subscript 2 would be 2 minus 1 over 2. And 2 minus 1 is just 1, so 1/2. B subscript 3 is 3 minus 1 over 3. 3 minus 1 is 2, divided by 3. B subscript 4 is 4 minus 1 over 4. 4 minus 1 is 3, and that's still over 4. Finally, B subscript 100 is 100 minus 1 in the numerator divided by 100 in the denominator, So you'll do 99 over 100. And finally, one more, a sub n equals negative 1/3 to the n. So the first term is negative 1/3 to 1. Anything raised to the power of 1 is whatever that base is, so it'll be negative 1/3. Now let's do a squared. That's negative 1/3 squared. A negative raised to an even power becomes positive. 1 squared is 1, 3 squared is 9, so positive 1/9. A sub 3 is negative 1/3 to the power of 3. That's raised to an odd power, so a negative raised to an odd is negative. 1 cubed for the numerator is 1, and in the denominator that's 3 cubed. 3 times 3 times 3 is 27. A sub 4 is negative 1/3 to the power of 4. A negative raised to an even makes it positive. 1 to the 4th is still just 1. 3 to the 4th is 3 times 3 times 3 times 3, which would be 81. And a sub 100, that's the 100th term. That would be negative 1/3 to the power of 100. We know it's going to be a positive because the negative is raised to an even power. 1 raised to the power of 100 is still just 100, and we'll write 3 to the power of 300. Roman numeral 2, recursively defined sequences. A recursive sequence is a sequence in which the nth term of the sequence may depend on some or all of the terms preceding it. Exercise 2. Find the first 5 terms of the sequence defined by a sub n equals a sub n minus 1 plus a sub n minus 2 and a sub 1 equals 1 and a sub 2 equals 2. This problem already gives us the first 2 terms. A sub 1 is 1 and a sub 2 is 2. Now we'll use the recursive definition to determine a sub 3. A sub 3 is equal to a sub 3 minus 1 plus a sub 3 minus 2. Let's perform the arithmetic in the subscripts. That will give us a sub 2 plus a sub 1. Now let's replace those subscript notations with its corresponding numerical values. A sub 2 equals 2 and a sub 1 equals 1. So 2 plus 1, the third term of the sequence, is 3. Let's find the fourth term, or a sub 4, using the recursive definition. That's equal to a sub 4 minus 1 plus a sub 4 minus 2. Let's perform the arithmetic of the subscripts. That will give us a sub 3 plus a sub 2. We just computed a sub 3. That value is 3. So we'll have 3 plus, and the a sub 2 given in the statement of the problem is 2. The sum of 3 plus 2 is 5. And finally, we need to solve for a sub 5. A sub 5 is, let's mimic the pattern that we've established for a sub 3 and a sub 4. That's going to be the sum of a sub 4 plus a sub 3. A subscript 4 we just computed as 5. A subscript 3 we computed as 3. The sum of 5 and 3 is 8. So the first 5 terms of the sequence are 1, 2, 3, 5, and 8. Find the first 11 terms of the sequence recursively defined by f sub 1 equals f sub 2, so the first two terms equal each other, and that equals 1, and f sub n is equal to f sub n minus 1 plus f sub n minus 2. So we're given the first two terms, that's a help. F sub 1 is 1. F sub 2 is also 1. Let's go ahead and write out f sub 3 using the formula. That would be f sub 3 minus 1 plus f sub 3 minus 2. So that's f sub 2 plus f sub 1. Okay, the nth term is the sum of the two previous terms. So let's continue with that. That would be, we were given 1 for the second term, 1 for the first term, so f sub 3 is equal to 2. All that work for 2. Let's try f sub 4. That's going to be the sum of the two previous terms, so that's f, third term, and the second term. The third term we computed as 2, and the first term was 1, so the fourth term is 3. I'm going to list the numbers just in case we start to see a pattern. So we've got 1, 1, 2, 3. Okay, I don't really see a pattern yet, but I've already voiced that. The pattern. F sub 5 is the sum of the two previous terms, so it would be f, the fourth term, plus the third term. The fourth term was 3, the second term was 2, so the sum is 5. The sixth term is the sum of the two previous terms, so the fifth term plus the fourth term. The fifth term was 5, the fourth term was 3, we got 8. The seventh term is the sixth term plus the fifth term. The sixth term was 8, fifth term was 5, so 8 plus 5 is 13. Let's do just a few more, and then we'll do this without actually using the formula. So the eighth term is the sum of the two previous terms, which would be the seventh term plus the sixth term. So 13 plus 8 is 21. The ninth term is the eighth term plus the seventh term. The eighth term was 21. The seventh term, 13. And 21 plus 13 is 34. And so even if we don't write this out, we can add the two previous terms to get the subsequent one. So 21 plus 34 gives the 10th term, which was 55, and 34 plus 55, which is 89, gives the 11th term. So we can say the 10th term was 55, and the 11th term, 89. The Fibonacci sequence, given as 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, comma, ... was named after the 13th century mathematician who used it to solve a problem about breeding rabbits. Roman numeral 3, partial sum of a sequence. For the sequence a sub 1, a sub 2, a sub 3, a sub 4, comma, ... a sub n, comma, ... the partial sums are s sub 1, which is just the first term, a sub 1. The second partial sum, denoted as s sub 2, is the sum of the first two terms of the sequence, a sub 1 plus a sub 2. The third partial sum, s sub 3, is equal to the sum of the first three terms of the sequence, a sub 1 plus a sub 2 plus a sub 3. And the fourth partial sum, denoted S sub 4, is equal to A sub 1 plus A sub 2 plus A sub 3 plus A sub 4, or the sum of the first 4 terms of the sequence. And if we're looking for the nth partial sum, S sub n is equal to the sum of the first n terms of the sequence. S sub 1 is called the first partial sum. S sub 2 is called the second partial sum, etc. S sub n is called the nth partial sum. The sequence S sub 1, comma S sub 2, comma S sub 3, comma dot 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 S sub n, comma dot 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 is called the sequence of partial sums. Find the first 4 partial sums and the nth partial sum of the sequence given by B sub n equals 1 over the quantity n plus 1 minus 1 over the quantity n plus 2. In order to find partial sums, we have to first find the specific terms of the sequence. So let's find them. B sub 1, the first term of the sequence, is 1 over 1 plus 1 minus 1 over 1 plus 2. That would be 1/2 minus 1/3. Let's continue. The second term of the sequence is 1 over, where the n was, we'll put in 2, so 2 plus 1, minus 1 over 2 plus 2. And so 1 over 2 plus 1 is 1/3, minus 1 over 2 plus 2 is 1/4. The third term, B sub 3, would be 1 over 3 plus 1 minus 1 over 3 plus 2. Looks like 1/4 minus 1/5. I'm hoping to see a pattern here. Do you see one yet? So B sub 4 is 1 over 4 plus 1 minus 1 over 4 plus 2, which would be 1/5 minus, yeah, you're right, 1/6. Okay, now that we have the terms of the sequence, okay, B sub 1 is 1/2 minus 1/3. B sub 2 is 1/3 minus 1/4. B sub 3 is 1/4 minus 1/5. B sub 4, the fourth term of the sequence, is 1/5 minus 1/6. There is a reason why I'm not combining those fractions yet, and it'll become very obvious when I do the sequence of partial sums. If we do the first sum, okay, that's just the first term, so we didn't get a whole lot of information here. But let's do the second one. The second sum, partial sum, is the sum of the first term, which is 1/2 minus 1/3, plus the second term, which is 1/3 minus 1/4. The third partial sum is the sum of the first term, which is 1/2 minus 1/3, plus the second term, which is 1/3 minus 1/4, and the sum of the third term, which is 1/4 minus 1/5. And let's do the fourth term, which would be 1/2 minus 1/3, that's the first term, plus 1/3 minus 1/4, which is the second term, plus 1/4 minus 1/5, which is the third term, plus 1/5 minus 1/6, which is the fourth term. Now, a couple of nice things happen. Let's begin by looking at the second partial sum. The negative 1/3 plus 1/3 cancels each other out. Let's look at the third partial sum. Minus 1/3 plus 1/3, minus 1/4 plus 1/4. Then let's look at the fourth partial sum, which is minus 1/3 plus 1/3, minus 1/4 plus 1/4, minus 1/5 plus 1/5. I'm out of space here, so I'm going to go to another page and just list what we got. So we got that the first partial sum is 1/2 minus 1/3. The second partial sum, when simplified, is 1/2 minus 1/4. The third partial sum was 1/2 minus 1/5. And the fourth partial sum, when simplified, is 1/2 minus 1/6. We're asked to come up with the formula, or the nth partial. And so what we do notice for the first partial, second partial, third partial, and the fourth partial sums is that we start with 1/2. And then we're going to have minus 1 over, and we need to find a relationship between the subscript and the number in the denominator of the second term. So we notice that for 1, the subscript, the number in the denominator of the second term is 3. That's 2 more. For 2, the subscript, the number in the denominator of the second term is 4. That's 2 more than the subscript. For the third partial sum, the number in the denominator of the second term is 5, which is 2 more. And so we recognize that the nth partial sum is going to be 1/2 minus 1 over the quantity n plus 2. Roman numeral 4. Sigma notation and the properties of sums. Given a sequence a sub 1, a sub 2, a sub 3, a sub 4, comma, ... we can write the sum of the first n terms using summation or sigma notation, which derives its name from the Greek letter sigma. The notation is used as follows. We write the big sigma, and in the subscript, we write k equals 1, and then we go above the sigma notation to write n. We write a sub k equals a sub 1 plus a sub 2 plus a sub 3 plus ... plus all the way to the nth term, a sub n. The left side of the expression is read the sum of a sub k from k equals 1 to k equals n. The letter k is called the index of summation, or the summation variable, and the idea is to replace k in the expression after the sigma by the integers 1, 2, 3, ... n, and add the resulting expressions. Properties of sums. Let a sub 1, a sub 2, a sub 3, a sub 4, comma, ... and b sub 1, b sub 2, b sub 3, b sub 4, comma, ... be sequences. Then for every positive integer n and any real number c, we can complete each of the following properties of sum. The sum of k equals 1 to n of a sub k plus or minus b sub k is equal to the sum of k equals 1 to n of a sub k plus or minus the sum of k equals 1 to n of b sub k, and the sum of k equals 1 to n of c times a sub k is equal to c times the quantity of the sum of k equals 1 to n of a sub k. Write the sum without using sigma notation. The sum k equals 1 to 4 of the square root of k minus 1 quantity divided by k plus 1. So we're going to expand this, and we'll put in the numbers as we go through the index. This will be equal to the square root starting at k equals 1, 1 minus 1, divided by 1 plus 1. Let's continue. Now we'll go to k equals 2. So we've got 2 minus 1 over 2 plus 1. K equals 3. Be 3 minus 1 over 3 plus 1. And finally, k equals 4, which would be 4 minus 1 over 4 plus 1. Let's do the rudimentary arithmetic. So we'll have 0 over 2 square root plus the square root of 1 over 3 plus the square root of 2 over 4 plus the square root of 3 over 5. Let's go ahead and take care of the first term, which is just 0. And the rest of it we can leave as is, or you can write it as 1 over the square root of 3 plus the square root of 1/2 plus the square root of 3/5. However, the second line of the way we wrote the expansion is usually sufficient. Write the sum using sigma notation. 1 minus 2x plus 3x squared minus 4x cubed plus 5x to the 4th plus ... negative 100x to the power of 99. In order to write the sigma notation, it is always helpful to find the nth term first. So in order to do that, I'm going to modify the first term and write it as 1 x to the 0. And the second term, I'm going to write it as 2x to the 1. I'll go ahead and write the rest of them. So I got 3x squared minus 4x cubed plus 5x to the 4th. And what I wanted to do in expanding or changing the way I wrote the first two terms is to be able to see a pattern. Let me tell you the pattern that I now see. The coefficients are 1, 2, 3, 4, 5. They increase by 1. The powers and the exponents go 0, 1, 2, 3, 4. They increase by 1, but we notice that the powers is 1 number less than the coefficient. So we're good with that. We also have to make an accounting for the alternating signs. And so let's start with by looking for the nth term. Okay, we've got n x to the n minus 1. That's cool. That works. We have to do something about the signs changing. One of the options is to do negative 1 to the n. So let's see what happens. For the first term, if I do negative 1 to 1, I get a negative sign. That's not what I want. I need it to start with a positive. So the quick trick to fix that is just do it n plus 1. Then instead of alternating negative, positive, we get to start at positive. So we alternate positive, negative, positive, negative. It's always a good idea to check. What do I mean by that? So let's count. I got 1, 2, 3, 4, 5. I want to make sure that if in this formula, the nth term formula, I check the fifth term, that's negative 1 to the 5 plus 1, 5x to the 5 minus 1, we simplify. I have negative 1 raised to the 6, 5x to the 4th, and negative 1 to the 6th is just positive 1. I get 5x to the 4th, and I at least have a check for the fifth term. It's a good thing to always do that. Now let's use the summation notation. So we'll do the summation of, I'll pick my index of summation as j. So we'll start at j equals 1, negative 1 to the j plus 1, and then j times x to the j minus 1. And we have to decide, do we go up to 100 or up to 99? And I'm going to check with 100, and that'll work, because the power of the last term will be 99.